All right, hello everyone. Today we are going to be going through the Systems Objective-Based Review Study Guide for solving systems of linear equations. So, in essence, what I'm going to do is what I am going to do is I'm going to work through this entire packet, breaking down every problem step by step and into simple forms. All right, and then hopefully you can use this as an additional resource as we prepare diligently for the test. So I'm going to start by putting my name on this. And I should note that I am using a pen. I recommend everyone to use a pencil. The reason I'm using a pen is I think with this camera and the light, hopefully for visibility purposes, okay? But I would always recommend using a pencil. All right, so number one, objective, I can rewrite functions in slope-intercept form. So what I would do if I was taking this is I know slope-intercept form is y equals m times x plus b, and I know that I need to get these four equations in this form, okay? And key key part about this is that the y variable needs to be totally isolated. When we say isolated, we mean completely by itself. All right, so let's look at number one. I have 4x plus 8y equals 24. I'm looking to get the term with y in it by itself, in this case 8y. So in order to do that, I am going to subtract 4x on both sides, which leaves me with 8y equals, now here 24 and negative 4x, those are not like terms because this term does not have an x in it. Hence, I'm left with negative 4x plus 24. Now for my last step, I need to, again, the y needs to be totally by itself. So I'm going to divide every term by 8 because I'm doing 8 times y, and the inverse of multiplication is division. Thus, I'm left with y equals, now here, I would do this in a calculator, so negative 4 over 8. As a fraction, we can reduce that in our calculators. We get negative 1/2 times x, and then 24 divided by 8 is 3. All right, and that's my final answer. So I'm going to go ahead and circle it. All right, on this one, similar idea. I have y minus 7x equals negative 9. Let me go ahead and draw my earthquake line. Again, my objective is to get the y variable totally isolated by itself. I notice that I'm subtracting 7x from both sides. So I need to get this term, negative 7x, on the other side. I can't simply just move it. I have to take this process algebraically. So to get rid of a negative 7x, I need to add 7x to both sides. Hence, I'm left with y equals, because this cancels out here, I'm left with y equals, and then 7x minus 9. Again, you cannot combine negative 9 and positive 7x, because those are not like terms. Again, to clarify, the negative 9 does not have an x by it. All right, next one. I've got 45 plus 5y equals negative 2x. So little different form than these first two. In this case, the negative 2x is on the right side, and our constant term, or just the number 45, is attached to the term with y in it, in this case 5y. So the first step I'm going to take, again, my objective is to get y by itself, so I want to get 5y by itself first. So in order to do that, I need to get rid of positive. This is a positive 45. So I'm going to go ahead and subtract 45 from both sides. And I'm left with 5 times y equals negative 2x minus 45. And then my last step, I need to undo this multiplication here, 5 times y. So I'm going to go ahead and divide every term by 5, which then leaves me with y equals, now this might be an error that some people might incur, and we want our slope, we've talked about this in class many times, we want our slope to stay as a fraction, and the justification for this is that it's much easier to graph a slope, graph a function, when our slope is in fraction form than decimal form. And I can't reduce negative 2/5 any further, so I'm going to leave it as y equals negative 2/5 times x, and then negative 45 divided by 5, that's negative 9. Hence, I'm left with this. Y equals negative 2/5 x minus 9. Okay. Next one and last one, we have 6y equals negative 18x plus 36. Could argue that this is the easiest of the four, as I already have the term with y in it completely isolated. And so all I need to do is get rid of the 6. And in this case, the 6, we're taking 6 times y. And the inverse of multiplication is division. Hence, I need to divide every single term by 6. Thus, I'm left with y equals negative 18 divided by 6 is negative 3x, and then positive 36 divided by 6 is positive 6. There we go. All right, so that was my first step, or my first objective. Okay. All right, let's go on to, sorry, let me move a couple things. Let's go on to part 2. I can identify solutions to a system of linear equations. So all we have to do here is plug an ordered pair into both functions. So I'll go ahead and draw a bit of an arrow. And if it satisfies both functions or both equations, then I know that my ordered pair is a solution. So I'm going to go ahead and walk through an example. The first thing to notice, or first thing to take note of, is that an ordered pair is in the form x comma y, right? So I'm going to go ahead and plug 4 into my, so we'll call this function a. So I'm going to say y, which in this case is 2, 2 equals 4 minus 2. And does 4 minus 2 equal 2? Yes, it does. So it satisfies the first equation, because when I say satisfy, it means both sides of the equation are equal. And let's go ahead and test it out for the second one. So I'm going to say y, again, y is 2, so I'm going to plug in 2. Does 2 equal 3 times 4 plus 4? Well, 3 times 4, that's 12. 12 plus 4 is 16, and 2 does not equal 16. So even though it satisfied this first equation, it certainly did not satisfy the second equation, so we can confidently fill in no, bubble in no. All right, next one. Again, following the same process here. So I'm going to go ahead. I always like to label that way. Just labeling makes it very, very clear what I need to do and which value is what to try and avoid any potential accidental errors. So I'm going to plug it into my first equation. My y is 9. 9 equals 2 times 3 plus 3. So 2 times 3 is 6. 6 plus 3 is 9, and 9 equals 9. So good start. Good start. On our second equation, we'll go ahead and plug in 9 for y. 9 equals 4 times 3 minus 3. And 4 times 3 is 12. 12 minus 3 is 9. And 9 does indeed equal 9. So it satisfied both equations. Hence, we can say that it is a solution to the system. Right? All right, next one. Again, following the exact same process. Actually, you know what? Since this one is very similar to this, in sake of the time video or time of the video, let's hop to this one. This one's slightly different, so bottom right. Again, I like to label my point x comma y. So when I plug it into this first one, I'm going to say again I see that my 2 is my x and my 12 is my y. So I say 12 equals 5 times 2 plus 2. I'm left with 12 equals, well, 5 times 2 is 10. 10 plus 2 is 12. And 12 does indeed equal 12. Now this first one, it's not in slope-intercept form. Okay, it's not in slope-intercept form, but that's okay. We can still plug the values in. So I can say 4 times 2 minus, and y would be 12. So 4 times 2 minus 12, does that equal 0? Well, 8 minus 12, as I think you might be seeing, this does not equal 0. So this is not a solution, right? So again, on a problem like this where it's slightly different, particularly this second equation, it's okay. You can still plug the values back in. And the key concept here is do both equations become satisfied, or do both sides of the equation become equal when I substitute, or you might say plug in, this coordinate value. So in this case, 3 comma 9, x comma y. All right, let's take a look at the backside. Let's do this. Let's do these two. These two kind of are a little more rigorous than the other two. All right, and the reason I mention that is if you look at this one right here, top right. Oops, sorry, let me scooch it down. This second equation is not already in slope-intercept form. The y is not by itself. So what I'm going to need to do is going to need to subtract 4 on both sides, which leaves me with y equals 2/4 x plus 4. And this is a little tricky right here. 2/4 can actually be reduced to 1/2. So I can say y equals 1/2 x plus 4. Now to go on and graph it, I'll graph this one first. So my y-intercept, my b value is 3, so up 1, 2, 3. I'm going to take great care in ensuring my points are accurate. And my slope, if my slope is 1 over 2, I could think about that as up 1 over 2. So up 1 over 2, 1 over 2. And it's also beneficial to recognize that a slope of 1 over 2 can also be considered as negative 1 over negative 2. So down 1 to the left 2. The reasoning for this is that negative 1 over negative 2 actually simplifies to 1 over 2. Okay, so I'm going to go down 1 over 2. All right, I'm going to get my ID. See if I can get this to work. Oops, second. Always another great reason to always wear your ID and have your ID is it is a great tool for math, especially when graphing. Okay, it's a pretty straight line. Not my best, but pretty good. Okay, so I graphed my first one. Let's graph my second one. I have 1/2 x plus 4. All right, so my y-intercept 4, I go up 1 to the right 2. And then again, I can also think about this as down 1 to the left 2. Then again, down 1 to the left 2. So let's go ahead and create that line. And you may be recognizing by now that these lines are indeed parallel. And we proved it by graphing. When I say parallel, I mean that, this line will never cross that line. But we could also recognize that, and both of these slopes are identical. Okay, but our y-intercepts are different. Hence, these lines can go on forever and ever and ever, but they will never intersect. And because they never intersect, we are going to say no solution, or we could put that symbol if we want to be fancy. Okay. So again, I think a common error on something like this would be interpreting this graph as saying, well, the lines go on forever and ever, which I agree. Yes, definition of a line, they go on forever and ever. But the question is, do they cross? That's the critical part, is do the lines cross? Do they intersect? Okay, and as you can tell from the graph and then sort of proven that the slopes are identical, they will never cross. All right, let's take a look at this one. So I have, again, I chose this one because this second equation, it's not in slope-intercept form. It's close, but I have this coefficient 3. I've got a 3 attached to the y. So in order to get the y totally isolated, I'm going to go ahead and divide every term by 3, as the inverse of multiplication is division. Hence, I'm left with y equals 2x plus 4. Now, when I graph this first equation, I'm really graphing this second equation as well. Okay, so my y-intercept of 4, 1, 2, 3, 4. And this is something I really want to point out, bring attention to. A lot of people, when they see a slope of 2 over 1, and they're working on a graph like this, they think, well, wait a second, I can't go up 2 because I'm outside of the graph. That's okay. Again, similar to this concept here, we can think about this as negative 2 over negative 1, hence down 1, or excuse me, down 2 to the left 1. And I should probably also put on here slope. M is slope equals y over x, or the change in y over the change in x. Okay, so I'm going to go down 2 to the left one, down 2 to the left one, and we'll keep it there at 3 points. Actually, try and be extra precise. Give a fourth point. All right, and I'm going to get my ID. I can try and line it up. This looks pretty clean. All right, close enough. And I graphed both of these. They're the same thing. These equations, this equation here and this equation here, they're exactly the same thing. So they are directly on top of each other. They are lying directly on top of each other. So this would be an example of IMS, or this symbol, representing infinitely many solutions. And just as a quick aside, the reason we say infinitely many is because the lines are identical. You could think about it, they're intersecting constantly. They're one and the same. There's no difference between the two. So any solution that works for this equation is automatically going to work for this equation because they're the same equation, right? So it sort of follows that any point we pick on here is going to satisfy or make both of these equations equivalent on both sides. And let's do this one too. Let's do this last one. I love fractions. Fractions are awesome. Okay. Let's graph this first function, y equals 1 half x plus 5. Okay, so y-intercept is 5. And again, I think, just to reiterate this, I think a lot of people, when we see a slope of 1 half, we automatically think, okay, I have to go up 1 to the right 2, but then we say to ourselves, well, this point isn't on the graph, so how can I graph this function? Right, that's okay. Again, I can think of it as -1 over -2. So down 1 to the left 2, down 1 to the left 2. So I'm going to go ahead and graph that. Now, some people might be wondering, like, how can I check to make sure that my slope is correct? Like, how can I make sure that I graphed it correctly, right, when using, this technique, kind of rewriting it? Well, my initial slope is positive, so my slope should be increasing. Think about like going up a mountain. And I could visualize our skier Bob, okay, skier Joe. Can't remember what we called that skier, but it does indeed look like they're going up an incline. They're going up a mountain. All right, and then our next one, y equals -5 halves x minus 1. B for begin, my y-intercept. I'm going to go to -1. So I can think about this again. 1, 2, 3, 4, 5. Uh-oh. I'm outside the graph. That's okay. We can think about -5 over 2, meaning down to the right. We can also think about that as 5 over -2. Okay? They're both negative values. It's just I'm placing my negative sign here in the top, and here I'm placing it in the bottom. So I can go up 5, 1, 2, 3, 4, 5, to the left 2. Okay, and I think we can see that our point of intersection becomes very clear. Sorry, let me line it up. All right. All right, and my point of intersection, let me be very careful as I count this. So I count across the x-axis first. So I go to the left 1, 2. So I know my x value is -2. My y value is 1, 2, 3, 4. Okay, and I'm going to go ahead and circle my answer and try and make it very clear to my instructor what my answer is. You know what? We should also do that on these two. There we go. Circle, and then circle. Perfect. All right. Let's talk about these. The fourth I can statement, I can estimate the number of solutions, or I can estimate the number of solutions to a system by inspection. And we could even wager saying I can identify the number of solutions. We don't have to necessarily estimate. Okay. So the process for this, I'm going to kind of walk through it. So the first thing I look for is, are the slopes the same? And if the slopes are different, I automatically, without hesitation, without question, can objectively identify this as one solution. And the justification is because the slopes are different. It does not matter, and I want to really draw attention to this. It does not matter If the y-intercepts are the same or different, it doesn't matter. If the slopes themselves, if these values right here, if they are different, you can stop right there and automatically justify a response of one solution purely because the slopes are different. Right, and just quickly, a justification for this is that if you have two lines, right, and their slopes are even slightly different, like let's even say they're just ever slightly so different, they're going to intersect. Okay, they're eventually going to intersect. Even if you have a line starting up here and it's skewed downwards a little bit, and you have a slope here that, heck, let's even say the slope is horizontal, it's eventually going to cross about, let's run off the screen, but in this area here. Okay, so that's the justification. All right, let's look at this second one. And immediately I am noticing this second equation right here is, actually, I'm going to lower this a little bit. Okay, this second equation here is not in slope-intercept form. I need to get the y by itself, so I'm going to subtract 3x on both sides, which leaves me with y equals negative 3x minus 2. Okay. I notice that my slopes are the same in this equation and that equation, slope of negative 3. But my y-intercepts are different. So this is a case of no solution because the justification is the slopes are the same, but y-intercepts are different. I'm going to go ahead and abbreviate. Okay, and here's a great example of this is up here. So this equation, y equals 1/2 x plus 3 and y equals 1/2 x plus 4, okay, so right here and here, they have the same slope, but the y-intercepts are different. And as you can see, no solution. And our last one, we could maybe take a testing methodology and infer that it's going to be infinitely many solutions. So let's see if that's right. Okay, so my first equation, I've got y minus 4 equals 5x. I need to get the y by itself. So if I add 4 to both sides, I get y equals 5x plus 4. And then my last one, I'm going to divide every term by 2, kind of building off what we practiced earlier, which leaves me with y equals 5x plus 4. And sure enough, both the slopes and the y-intercepts are exactly identical. So we can say infinitely many solutions, okay, because the slopes and y-intercepts are the same. Okay, oh, sorry. So these problems right here, I personally kind of like doing these a bit more than graphing, because when we have the knowledge about analyzing a function or analyzing an equation purely by looking at the slope and y-intercept, right, it makes our job a little bit easier for us, a little bit easier. Okay, so that's page 1. So here's what I'd like to do, again, just to with respect to time's sake of the video, I'm going to try and we'll pick 2 from here. All right. I think doing a fraction one would be a great idea. We love fractions. And this one's also good, bottom 2. Okay. All right, so let's take a look at this first one. And actually, let me write this up here. I'll put a big star. Like if I was studying, I would write this. All, or we could say both, equations must be in slope-intercept form, or y equals m times x plus b. Right? And in looking at this bottom left one, I can see that both of these equations are not in slope-intercept form. Uh-oh. Okay, so here's what I'll do. I'm going to spend this little workspace here and rewrite the first equation. Okay. Now, I need to subtract 8 from both sides because I want to get the 2y by itself. So I'm left with 2y equals, we'll say 8 minus, excuse me, x minus 8, I apologize. Now I'm doing 2 times y. The inverse of multiplication is division, so I'm going to go ahead and divide every term by 2. I'm going to be left with y equals negative 8 minus 2, or divided by 2 is 4. Now here, remember, there's that ninja 1 in front of the x. So I'm going to be left with 1 over 2 times x minus 4 equals y. And you may be saying, well, wait a second, that's not in this form, okay? Well, again, we could just rewrite it like this. I'll write it write it off to the side. Y equals, and just when you're rewriting it, just think about, okay, this is positive 1/2 x, so 1/2 x minus 4. It's my first equation. All right, for my second equation, I'll go ahead and write it off here. I have 5x minus 3y equals 75. Well, in order to get the y by itself, I first need to start by getting the negative 3y by itself. So in order to do that, I'm going to go ahead and subtract 5x from both sides. And I'm left with negative 3 times y equals, and I'm going to write this as negative 5x plus 75. I think a lot of people may instinctively write it as 75 minus 5x. Again, not wrong, but it kind of helps, again, further our goal of getting it into this form. Now what I need to do is divide each term by negative 3. Okay, and I'm going to be left with y equals, well, negative 5 divided by negative 3, that's positive 5/3 x. And then 75 divided by negative 3, that's negative 25. That's our second equation. So now I've rewritten both of these equations, and I'll kind of match it up for you guys as well. So equation 1, equation 2, equation 1, and equation 2. Right, now what I need to do is I need to set both of these equations equal to one another, or I guess one way to think about it is set the side that's opposite y equal to the side that's opposite y in the other. So I'm going to be left with 1/2 x minus 4 equals 5/3 x minus 25. And kind of as we reviewed the other day in class, there's multiple ways you could go about this. You could even argue an infinite amount of ways we could go about this. Here's what I'm going to do. I think most of us are accustomed to, in this case, probably, I'm presuming most people would probably want to subtract 1/2 x from both sides. Okay, so that's going to leave me here with negative 4. On a part like this, okay, so why does 1/2 x minus 1/2 x equal 0? You could think about it, this analogy. If you have half of an X-ray, or half of a machine, or heck, let's do half of an apple. Let me see if I can draw an apple. Okay, so we'll kind of go like this. There's like the core, and there's the stem. Okay, excellent, incredible drawing skills. So we have half of an apple, and if we take half of it away, there is no apple. Hence, 1/2 x minus 1/2 x is 0, or just, again, it cancels out. We're left with negative 4. Now here, you would have a calculator for this. I'm just going to kind of show my work here at the bottom, but I would of course recommend doing it with a calculator. Common denominator of 6, so 5/3 would be re-expressed as 10/6. And here we'd need to multiply by top and bottom by 3, so I'd get minus 3/6. Okay, which then leaves me with 7/6, so I'd have 7/6 x minus 25. Again, if you're doing a computation like this, don't do that in your head. Definitely take the time to use a calculator. I'm going to add 25 to both sides, and I'm left with 7/6x. Okay, negative 4 plus 25 is 21. I'm actually going to write that as a fraction, 21/1. Now again, I think most people here are going to decide to divide by 7/6 and do 21 divided by 7/6. Again, totally acceptable. I'm just going to show that you could also multiply by the reciprocal. So I'm going to flip this fraction of 6/7. Okay, and x equals, well, here I can This cross reduces. 7 and 21 reduces to 3 and 1. And I'm left with x equals 18. But I'm not finished yet. I need to plug it back into my original equation. All right, I'm going to go ahead and plug it back into, let's plug it back into this first one. All right, and when I do that, I'll kind of show my work over here. So I'm going to get y equals 1/2 times 18 minus 4. That's y equals 9 minus 4, y equals 5. And sort of like our insurance policy, we can also plug it into this one. Okay, so segment it off. Y equals 5/3 times 18 over 1 minus 25. So y equals, this cross cancels, 1, 6. So this is 30 minus 25. And indeed, y does equal 5. So then my final solution is going to be an ordered pair of, oh, perfect, we'll keep it in this space right here. We're going to say 18, comma, 5, and parentheses, okay, and hopefully this can show our instructor this is the answer. I think it provides pretty clearly to us, okay. All right, so I would actually argue that that was the most challenging one. I think, again, kind of looking at time of where we're at, in the interest of the video, let's take a look at, let's do this one. Let's do number 6. I can solve real-world problems using systems of equations. All right, so one sales position pays $500 per week and $2,500 for a sign-on bonus. A sign-on is meaning that it's a one-time additional pay, but it doesn't happen over and over again. The other sales position pays $250 per week and a $6,000 sign-on bonus. So I think this is a great problem in the fact that, later on in life, when you're looking at acquiring a job, and you're trying to analyze finances, you're going to be able to say, okay, well, in the long run, what's going to net me more money, or after how many months are both going to be the same? Maybe it's something calculating a phone bill, who knows? But a lot of financial stuff, at least in this sense, is working in linear equations. So this is great problem. So I'm going to say y equals, so I have $500 per week, so 500 x, again, per every week. That's a clear giveaway for slope, plus 2,500. Same idea here, 250 per week, so y equals 250x plus 6 grand. In this case, x is representing number of weeks, y is representing income or dollar. So I'm going to go ahead and label my graph y-axis dollar, and x-axis we'll say is number of weeks. Right, so I'm going to go ahead and graph them. And let's do it this way. So my starting value for this one, for equation 1, is 2,500. And if you can see, I'm trying to see if you can see it on the screen. Even though I'm going up by increments of 1,000, I have this other tick mark line, or I have this other grid line, right? So if there's only one in between, it's implying that, okay, so up would be 500. So 1,000, 1,500, 2,000, 2,500, so that's my starting point for this one. And then my slope is 500 over 1. So I go up 500 over 1, up 500 over 1, and I'm being very, very careful that I'm lining it up, okay, with my tick marks on the bottom. All right, and we'll do one more. Up 500 over 1. Excellent. Go ahead and create my line, and I'm going to try and get it as precise as possible. Okay. That is, oh, if I can get it. Okay, that looks good. All right. Oh, barnacle heads, we curved it at the end. All right, so that was our first one, and then second one, starting point is 6,000. Now here, it's telling us to go up 250, but the problem with going up 250 is then Let me see if I can lower this even more to show you like how I'm thinking through this. Yeah, there we go. So if from here to here is 500, then 250 would be somewhere in the middle. And I don't know about you, but I don't like it when things are not precise. I like it to be very, very clear, this is on the mark or it is not on the mark. So what I'm actually gonna do is I'm gonna re-express 250, and I'll do it up here, 250 over 1 equals 500 divided by 2. So now I can work with the increments of 500. So I'm going to go up 500, but I need to go over 2, and I'm even going to be extra. So 2, and I know that it's 500. Trace my line, perfect. Oh, excuse me, yep, I got to be very, very diligent with this. 2, 500, very good, very good. So we'll go up 500 again. We'll go at 4. Okay, and it's 700. Very good. We'll go up at 500 again. So up, excuse me, up 500 over 2. So let me make sure I'm getting it lined up. And over 2. Bingo. Okay. Let's go ahead and construct the line. You know what it's actually looking like? That first line I'm going to have to redo. Try and get it lined up as close as I can. Perfect. Alright, there we go. Try and extend it even a little further. Okay. Let's cut off a bit. Okay. Here, let's extend the line. Try and get it lined up as precisely as possible. Okay. So again, this is an example of where precision is absolutely key. And I'm kind of tracing this point down, and I see that it's intersecting at the point 14, comma, and then this would be 9,500. Okay, good. All right, and one thing, like, I know some people are saying, well, how do I know? How could you check that? Two ways you could do it, kind of like we practiced earlier on these sorts of problems. You could plug the ordered pair back into both equations and see if it satisfies. Or I think this is a great example of where, math is one of those subjects requires precision, requires that attention to detail, meticulousness. Okay. So my solution is 14, comma 9,500. And let me just triple check that point of intersection is indeed lined up with 14. Absolutely, yes it is. Let me double check this. Okay, yep, that is absolutely lining up with 9,500. Good, very good, very good. Okay, so here, and it seems like with quite confusion with the 3 exclamation marks, which I always find hilarious. It says, what does my answer mean? What does it mean? And the simplest way to think of this is after 14 weeks, both people will earn $9,500. Okay. And you know what? Let's label this line as like person 1 or P1, and let's label this line as person 2. Okay. And let's call person 1, oh, heck, called Patrick for P. And then let's call person 2, I don't know, we could call her Sarah. All right. And it's asking who has more money after 2 weeks. So here at 2 weeks, I did not intentionally do that, but it does appear that I will have acquired more money after 2 weeks, right? And who has more money after 14 weeks? Well, neither of us. I would answer that. We both have the same amount. But I just kind of to cap off the video, I think, in taking this in a real world context, some people might be enticed by, oh, I'm getting more money like right off the bat. I want to take this deal. Look at that. I'm at $6,000. here at week 2, I'm way more than Sarah. But as you notice that difference, okay, I'll kind of even shade it in a little bit, or you could see maybe how I'm shading it. That difference becomes smaller and smaller. And then actually, if we were to extend this, you might be able to envision Sarah begins to overtake Patrick. So in the long run, Sarah's position is more profitable. In the short term, Patrick's position is more profitable. So again, this is just such a beautiful example of how, with linear equations, it really truly does help us in making informed decisions about the future. Okay, it allows us to make accurate predictions about what may or may not happen in the future. Okay. So anyway, I hope you enjoyed this video. The Can't really zoom out of the camera, but hope you enjoyed this video. I hope it was helpful. We'll also have the answer key on Schoology should you need, not should you need, when you should be checking your work against the other answers. Okay. And again, thank you for watching and have a great day. Bye.